See, the other day we discussed up to size of the atoms, and that includes ionic radius as well as covalent radius and all the types of various radiuses. So let us go to the next factor which influences the periodic properties, that is ionization potential. This is the minimum energy required to remove a loosely bound electron in ground state from an isolated gaseous atom. That is, if you take a gaseous atom, you remove an electron out of it, the amount of energy required to do that is called first ionization energy. Now, if once an ion is formed, if you remove one more electron, that would become second ionization energy, and so on. You will always notice that as the electrons are being removed, the size of the atom shrinks. It will become smaller and smaller, and therefore energy required to remove electron would start increasing. So E1 would be less than E2, less than E3, and so on up to En. And as the size decreases every time an electron is removed, and this is what you will notice. Ionization is an endothermic change. That means energy is required here, and it is generally measured in electron volts per atom or kilojoules per atom. What are the factors that influence the ionization energy? First, atomic size, and atomic size increases means ionization decreases. Z effective nuclear charge. If it increases, ionization increases. Screening factor increases, ionization decreases. Principal quantum number n increases, ionization decreases, which means lower orbitals require more energy compared to that of higher orbitals. Next, penetrating power. You know that SPDF, this is the order in which the penetrating power is for a particular orbital. So, as the penetrating power increases, ionization increases. Next, if you notice 2s and 2p, removal of 2s electron becomes difficult than compared to that of 2p electron. That's why exceptionally you will notice that beryllium will have more ionization than boron. Okay. Same logic applies to magnesium greater than aluminum. Okay. Here also beryllium. Second ionization, then now we are only removing from 2s1 versus 2s2. So in that case, boron will have more compared to that of beryllium. Okay. This is what is the exception you will identify in ionization. Next, half-filled and full-filled stability. Nitrogen has a half-filled stability of 2p3. Oxygen has for 2p4. Okay. And ionization, first ionization, you will notice that nitrogen is greater than oxygen, phosphorus is greater than sulfur, arsenic is greater than selenium. And the second will be reverse. Okay, this is another exception which you will identify, and this exception is due to the half-filled stability. Okay, usually P6 is the most stable state, then D10, then P3, then D5. Okay, then S2. After that, it is S2. Okay, this is the order in which you need to check out the stabilities. All right, next, trends of ionization energy from left to right. If you notice, lithium to neon, it is supposed to increase. This is what we expect. Okay, and down the group it should decrease. So what, where are the exceptions coming? See, boron and beryllium is an exception. Now beryllium is more than boron. Next, again you will see here nitrogen oxygen is an exception, where nitrogen is coming more than oxygen. Okay, so this is ionization trend. Exceptions, another exceptions are being gallium versus aluminium. Gallium will have greater than aluminium, and as gallium size wise, if you notice, aluminium is bigger. And all 5D elements will have greater ionization than 4D, like hafnium, mercury, gold. They will have higher first ionization compared to that of their elements present in 4D series. Correct? So you can see that size wise, lanthanum is more, but this is what the size is. We discussed this, and that's why ionization will vary this way: hafnium greater than zirconium, tantalum greater than niobium, osmium greater than rhenium, platinum more than palladium, gold more than silver, mercury more than cadmium. Okay. Now, for ionization, you will see metallic and non-metallic character inversely proportional to ionization. So that means more the ionization energy, more is the metallic character. Okay, metallic character will always increase, and if you have more non-metallic character, which means you have more ionization. So that is directly proportional. Reactivity wise, if you notice, if you have high reactivity, okay, based on metal reactivity, which means you have less ionization energy. Oxidation state wise, see, when you're going for a successive ionization, correct? And between the successive ionization, if it is the difference of energy is greater than or equal to 16 electron volts, then we can say the lower oxidation state is more stable. For example, sodium releasing an electron here, we require some x1 amount of energy. And Na plus releasing one more electron requires x2 amount of energy. And the difference between these two is 42.7, which means there is a huge difference in the energy here, which suggests the first ionization will always be more stable. First oxidation state, that is Na plus, will be more stable compared to that of Na2 plus. Okay. And if the successive energy between the two ionizations is less than or equal to 11 electron volts, in that case, the second oxidation state is more stable. Magnesium releasing one electron here, becoming Mg plus, and Mg plus becoming Mg2 plus. The difference in energy is only 7.4. Thus, we can say the second ionization is more stable compared to that of, second oxidation state is more stable compared to that of first oxidation state. In case of aluminum, the same logic if you check out for aluminum, it is Al plus 3, then plus 1, and then plus 2. Okay. This is the stability order. This is not ionization order. Remember, ionization will always be greater for higher oxidation states. Okay. So if you notice the entire order here, see left to right, this is the order: lithium, then boron, beryllium, carbon, oxygen, nitrogen, fluorine, neon. Group 13, gallium is almost equal to aluminium. Group 14, lead and tin are almost equal, very close by values here. Next, group 18, helium is the highest, then neon, and so on up to radium. Okay. So these are few ones which are typically asked, so just be careful with it. Next, check out reducing power. If if you have more electropositive character, that means it will have less amount of ionization energy. Got it? Notice the next term, which is electron affinity. Electron affinity is about the amount of energy released when one electron is added to the valence shell in its isolated gaseous state atom. So if X is an element on which electron has been added, then that will become X minus plus electron affinity. Here, energy released, right, which implies that electron affinity is positive. Required energy, if you notice, EA is negative or zero. Okay. We usually call electron affinity either in terms of negative or zero if there is no affinity at all. Okay. In case if there is no affinity. Now, if you notice electron gain enthalpy, it would be same as affinity, same as electron affinity, but with a negative uh, sign. That is, electron gain enthalpy will be equal to minus of EA. Second, electron affinity is always going to be negative for any element, because imagine it is already gained a negative charge and you are trying to push one more electron into it, so it won't accept it, which means naturally it will not accept unless you forcefully add those electrons. Therefore, electron affinity is negative here, or electron gain enthalpy is positive. Any successive electron affinity, if you notice, for example, first one may be positive or negative, but the second one is always negative. And the magnitude of second one is much, much higher than the magnitude of the first one. Okay. Therefore, overall sum is always going to be positive. Delta H electron gain enthalpy will always be positive. Let me show this with an example. When it comes to oxygen adding one electron releases minus 141 kilojoules per mole of energy. Next, adding one more electron to O minus, that would that we have to forcefully add 744 joules of energy. Okay, so you could imagine that the sum of these two is positive. Okay, so every time you observe that, this is what you will notice. And second thing, if you notice the electron affinity of oxygen versus electron affinity of sulfur. The first electron affinity, that is the energy released, will be much higher for sulfur. Okay. But if you notice the delta H value, because now delta H electron gain enthalpy for O minus versus delta H electron gain enthalpy for S minus, if you compare them, because this is also a positive term, now O minus will have more value compared to that of F minus. Okay, so keep that in mind. Right, next. If you see X plus 1 electron giving X minus, if this is electron gain enthalpy, then X minus, exactly if you write the reverse order, that is X minus trying to become X and releasing one electron, this is the ionization of X minus. Since the equation is same, the energy should be same. So therefore, this energy, which is released energy, is same as the required energy for X minus. Okay. Next, check out factors influencing electron affinity. Atomic size wise, larger the size, less is the electrostatic forces, so less energy is released. If Z effect is more, size is less, electron affinity is more. Screening effect is more, Z effect is less, size is more, electron affinity will be less. Next, when you have half filled or full filled stability, nitrogen has 1s2, 2s2, and 2p6. It will be highly reluctant to accept the electron here. So therefore, electron affinity for nitrogen is negative. And same logic applies to zinc. Zinc, it is 3d10. It will be highly reluctant to accept any electron. There also electron affinity is positive, but very, very less positive. Beryllium, it will not accept electron at all. That is also electron affinity being negative. Boron would accept electron with much easier way here. Okay. So all inert gases are extremely reluctant in accepting electrons. So what you need to remember is this beta. These are the ones which have a positive electron gain enthalpy or negative electron affinity value. So remember beryllium, magnesium. Then comes sodium, okay, helium, argon, neon, krypton, xenon, and radon. These are all the forms which you need to have. Clear? I hope this part is clear, everybody. Okay. Now notice left to right. Left to right, lithium will have the least amount of energy released, then compared to boron, then carbon, oxygen, and fluorine. Okay. Next, down the group. This is very, very interesting when it goes down the group here. Now you will see down the group there is a very Regular trend when it comes to lithium to cesium. Lithium to cesium, there is a regular trend. Group 2, we have a very different trend. Okay, sorry, let me rewrite that. Group 2, we have a different trend now. So in this case, you'll notice that barium is greater than strontium, is greater than calcium, is greater than magnesium and beryllium. In fact, magnesium and beryllium, if you notice, they both have, negative electron affinities. They both have negative electron affinities. Next, if you notice group 13, we have aluminum greater than boron, clear, which is, okay, slightly different here. Slightly, gallium will be slightly higher, okay, and boron will be less, just like in this group. So, aluminum, then comes gallium, almost same as indium, okay, then thallium, then boron. Okay, this will be the order. Next, here you will notice silicon is greater than carbon, greater than germanium, greater than lead and tin. Okay. Group 15 is exactly opposite. Okay. Group 15 is exactly opposite. Here. You will notice that just that bismuth is slightly, antimony and bismuth are almost the same. That greater than arsenic, greater than phosphorus, greater than nitrogen. Okay. In fact, sorry. Bismuth should be here, slightly greater. Bismuth is slightly greater than antimony, and then arsenic, phosphorus, and nitrogen. Now, whichever I ticked here, right, whichever I ticked here, that includes these cases. Okay, right, this one, especially beryllium, magnesium, nitrogen. These cases, you should notice them as the cases where they are always positive electron gain enthalpy or negative electron affinity. Okay, next. Group 16, group 16, you will notice that sulfur is highest, then selenium, tellurium, polonium, and last comes oxygen. Oxygen has the least value, very important to remember. This is the most asked ones. Direct trends, if anything that has been asked, is always from oxygen's end. Okay, and halogens also. Chlorine greater than fluorine, bromine, iodine, and acetylene. I hope these trends are clear. Everybody, please check. As per data, antimony is only given here. Sorry, slightly greater than bismuth. The values given is 103 and 95. Okay, so slightly greater. Done, everybody? Right. See, generally, period 3 elements have more electron affinity than period 2 elements of the respective group. So, if you notice nitrogen, phosphorus, oxygen, sulfur, fluorine, and chlorine, this is the way in which you have to check out the electron affinity cases. Now, let's see about electronegativity. The tendency to pull the shared pair of electrons in a covalent bond, that is called as electronegativity. Suppose I have a polar bond AB and there is a covalent bond between them. If electronegativity of B is greater than A, correct, then that B will get delta negative charge, A will get delta positive charge. Okay, and we say the polarity has developed. If electronegativity of A is greater than B, then A will have negative charge, B will have positive charge, and here also polarity has developed. In non-polar covalent bond, there is no polarity between them. Okay. Typical differences you can see. Electron negativity means It is with respect to an atom in a uh, molecule with a covalent bond. This is with respect to an atom in its isolated gaseous state. This is not energetic term. This is an energetic term. This is irregular. This increases regularly, but this changes irregularly. There are no units for electronegativity. This is measured in kilojoules per mole. This is a relative term. This is an absolute term. That is the main difference. Electronegativity, you can see the order. Fluorine has the highest electronegativity, followed by oxygen, chlorine, nitrogen. So this is the order that has been followed. So fluorine, oxygen, chlorine, nitrogen, bromine, sulfur, iodine, carbon, phosphorus, hydrogen. This is typical order of electronegativity. The order of electronegativity is something which will be useful throughout the topics, different topics. So you better remember this sequence, complete sequence, how it is. Okay. See, what are the scales for electronegativity? Millikan scale is average of electron ionization and electron affinity. That is Millikan scale. Okay, and that is measured in electron. I mean, energies are measured in electron volts per atom. And Pauling scale is always equal to Mulliken scale by 2.8. So whatever the value you will get divided by 2.8. So 2.8 in this case it will become 5.6 electron volts per atom. If I have to convert this electron volts per atom into kilocalories per mole, then I have to multiply that with 64.5. So that will give you kilocalories per mole. So this will be the electronegativity with respect to Pauling scale. Another scale that is being used is Alfred Rocho scale, which is AR means Alfred Rocho, which is Z effective E square by R square minus 0.359 Z effective by R square. Z effective is Z minus sigma, and Pauling scale is equal to Alfred Rocho scale plus 0.744. Okay. Z effective is calculated using Slater's rule. From Slater's rule, we calculate the Z effective. R value will be given to you. Substitute that, calculate X. Now let's see what are the applications of electronegativity. First, bond strength. Delta S increases, more electronegative difference will be there, which means more electrostatic attraction, and higher is the bond strength. Like HF, HCl, HBr, and HI. This is how the bond energy will be, which means bond strength is higher for HF. Then C double bond C will have more less bond strength than double bond and double bond O, because the electronegative difference is increasing here. More electronegative difference, more is the attraction. More the percentage S character, more is the stronger bond energy. Okay. So you can see here carbon has sp, this carbon is sp2, this carbon is sp3. So this carbon and hydrogen bond will be stronger compared to this carbon and hydrogen bond and this carbon and hydrogen bond. Okay. Right. Next, we know that how to calculate DAB, that is from Stephenson's formula. DAB is equal to RA plus RB minus 0.09 into delta X. Now you notice that the bond length is given as 1.44 angstroms. H2 is given as this much. Calculate HF. Electronegativities are given here. You put the difference of that, multiply with 0.09, right? RF, if this is the bond length divided by 2, that will give the radius of FF, radius of HH. Adding that, we'll get radius of HF. Okay. So learn how to use the Shoemaker formula. Next, charge on the ion. If you notice, more positive charge, more electronegativity, and more negative charge, less electronegativity. Electronegativity, O is greater than O minus, greater than O2 minus. Similarly, N2 plus is greater than N plus, N2 minus, and N3 minus. Fe plus 2 will have lesser charge compared to Fe plus 3. That means it has more electronegativity. Copper 2 plus has more electronegativity than copper plus, and so on. Now, oxidation states, higher the oxidation state means higher the electronegativity. So, manganese here is plus 7 oxidation state. This has more electronegativity compared to this manganese, and this manganese. Similarly, PCl5 has more compared to that of PCl3 and compared to that of PH3. If we have same oxidation state, then you have to check out the side atoms. So fluorine is strongly withdrawing. So phosphorus now will have more electronegativity compared to the phosphorus here, compared to phosphorus here and here. In HOCl towards HClO4, you notice that this chlorine has highest oxidation state, then this one, then this one, and then this one. CF4 will have more than CCl3, CBr3, and CA4 and CH4. The next application is about hybridization, which we, indirectly learned this, that if you have percentage S character more, electronegativity is more. So carbon with all four single bonds are sp3, double bond is sp2, single triple bond is sp. So sp carbon will be higher electronegative nature. Next, if ionization energy increases, electropositivity decreases, electronegativity increases. So electron affinity increases and electronegativity will increase. Now see, higher ionization and higher electron affinity will increase the electronegativity. Okay. Now quickly go through the groups, how the electronegativity is. See, group 13, boron is slightly more than thallium, then indium, gallium, and aluminum. Aluminum will have the least electronegativity. Remember that. Group 14, carbon is greater than silicon. Silicon, germanium, and tin are almost the same. Lead will be slightly higher. Nitrogen, phosphorus, arsenic, antimony, and bismuth will have almost the close electronegativity. Oxygen has highest here, then sulfur, selenium, tellurium, and polonium. Lastly, fluorine, chlorine, bromine, iodine. So fluorine will have the highest. So this sequence is about electronegativity. Next. Left to right, acidic strength depends always on electronegativity difference. Okay, if electronegativity difference is more, acidic strength will always be more. So you can see CH4, NH3, H2, and HF. You'll notice that HF is stronger acid, and this is how the trend would increase. The same logic applies to the next group also, next period also. Down the group, down the group, acidic strength depends upon bond dissociation energy and not electronegativity difference. So electronegativity difference will be more or less. You always need to judge on the basis of bond dissociation energy. So for example, if you take HF, HCl, HBr, and HI, then you'll notice that HF will have more bond dissociation energy. And similarly, HI will have more acidic strength in case of group 17. Next. Group 16, H2O is less than H2S, H2SC, H2TE, and H2PO. Okay. So this will be for group 16. Here, down the group, acidic strength increases. Now, group 15 also is the same thing, except that they have lone pairs and they are generally basic in nature. If they are basic nature to be determined, then ammonia is greater than pH3, then arsenic, antimony, and bismuth. Okay. Next, see what are also compounds. Generally, if an element central atom is connected to hydrogen via oxygen, then those are called oxo compounds. And oxo acids, for example, H2SO4, H3PO4, HOCl, these are all oxo acids. Now, they could break two ways in aqueous solution. Okay, either they can break as XO minus and H plus, which makes them acidic, or they can break as X plus and OH minus, they can become basic. As per the scientist Galley's, if you take XOH, if you take XOH or AOH And if AOH electronegativity difference is greater than 17 between A and OH, then AOH will have more ionic character. Hence, in water, this will split as A plus and OH minus. That's how it will split. And if A has electronegativity greater than 1.7, or which is non-metal, and electronegativity less than 1.7, then AOH will be either acidic or basic. You just need to check out whether they are acidic or basic. In AOH, electronegativity difference between Na and O, if it surpasses 1.7, the bond is ionic. So therefore, the difference in the sodium is only 0.9 and oxygen is 3.5. So the difference is sufficiently high, so that makes it basic. ClOH, the difference between chlorine and oxygen is less, but oxygen and hydrogen is quite more. So therefore, bond breaking can take place here. Here the bond breaking take place here. Clear? Next, see nature of oxides. Acidic character increases across the period. If you go from left to right, acidic character will always increase in the case of oxides. So you will notice B2O3, B2O3 relatively is less acidic than CO2 than NO2. And same logic works for next group also. Al2O3, which is amphoteric, is less acidic than SiO2, P2O5, SO3, and Cl2O7. And group 1, group 2 oxides generally form basic oxides except beryllium oxide, should be recognized as amphoteric oxides. Okay, these are the trends. Now notice amphoteric oxides. Beryllium oxide, Al2O3, Ga2O3, SNO, SNO2, PbO, PbO2, Sb2O3, H2O. Cr2O3, V2O5, MnO2, and ZnO, and Mn3O4. These are the oxides which you need to mug up everybody. This is a must-do question. Okay, this is compulsory question. Everybody should attempt and make it correct. Okay. Which of the following are amphoteric oxides? So remember this list. Okay, practice this list. Next, neutral oxides. Again, another important list. Which of them are neutral oxides? There are only four neutral oxides that includes H2O, CO, N2O, and NO. Next, if you notice HNO3, H2CO3, and H3PO4, it is based on oxidation state plus 5, plus 4, and plus 3. Higher oxidation state, more acidic character. Same way HOCl, HClO3, HClO3, and HClO4. Plus 7 is more oxidation state, so more acidic. H2SO4, it is plus 6, and here it is plus 4. That is how the acidic character will vary. Next. Oxides also same logic. Down the group, if you compare the electronegativity, phosphorus is more. So therefore, that will have more, acidic nature. Cl2O7, if you add it to water, it will become HClO4. That is stronger acid compared to that of HBrO4 or HiO4. In partial, in this kind of compound showing the oxo compounds here, so HOCl. That is, if you notice HOF here, the electronegativity difference for fluorine is very high. That's why this will make it more acidic in this case. Next, notice ionic character. According to Haney and Smith, we can directly find the ionic character as a percentage ionic character using this formula. 16 times of electronegativity difference plus 3.5 times of electronegativity difference whole square. Okay. If the difference is greater than 2.1, we will say it is ionic character. If it is less than 2.1, we call it as covalent character. According to this is a difference. It is only checking the electronegativity difference here. here according to Gallus. But if you notice the complete percentage ionic character in the bonds, you should check out for 2.1. Okay. So here it is about ionic bonds, here it is about ionic character. So characteristic will be more of ionic, but a complete ionic bond means you need to check out 2.1 value, electronegativity difference value. I hope all of you understood, and please remember what is Hane and Schmidt formula. Hydrolysis. If the electronegativity of X is greater than A, then hydrolysis products will be HX. Okay. So suppose if you have chlorine, chlorine has more electronegativity as compared to that of oxygen. Okay. Sorry. I mean as compared to that of boron. So in that case, this Cl and H will undergo as one product and boron will form boric acid as one product. Okay. PCl3, if you react with 3 moles of water, at that will become 3 moles of HCl and H3PO2. So the other day when the question came in exam, you couldn't last exam. A lot of you made this mistake. Check. If you have PCl3, okay, this was given in GTA, I guess. PCl5 it was given. So please make sure that the hydrolysis done is proper. In this case also, PCl3 plus 3 moles of H2O will give you 3 moles of HCl and POH thrice, which can be written as H3PO2. So we will have 3 moles of HCl as an acid and 1 mole of H3PO3 as an acid. PBr3 plus BBr2 and H2O. So that will become 2 HBr and POBr3. And POBr3 on hydrolysis will give you this. Next. If electronegativity of X is less than A, then that means if you compare to this and this, now this C itself is less than A, then Cl here and HO, these two will get connected and that will become HOCl instead of HCl, now it will become HOCl and rest will become H2. Everybody please go through these two factors once. Finish, everybody? I hope all of you got that. Not easy. See what are the important exceptions here. Density factors. Sodium is slightly greater than potassium, magnesium is slightly greater than calcium. Usually density should increase down the group, but that is an exception. Lithium as the lightest metal, light is dense, and you know, iridium and osmium, if we compare, iridium is slightly over edge to that of osmium. And check out group wise. Lithium to cesium, it is increasing order. Next, calcium to barium, if you notice, it is increasing order to this one. Lanthanum greater than yttrium greater than scandium, mercury greater than cadmium greater than zinc, copper greater than iron greater than chromium, hafnium much greater than zirconium than titanium. Done. Next, what is lattice energy? See, the amount of energy that is released when one mole of cation and anion combine to form one mole of solid crystal, that is called lattice energy. So Na plus Cl minus giving NaCl. The amount of energy released is lattice energy. It depends upon how much charge it has. So that will be Q1, Q2 by R. R will be simply addition of anion and cation radius. Check. Factors that influence the lattice energy. Intermolecular distance. As the lattice energy decreases, okay, lattice energy decreases as the radius will increase. LICL, if you notice, that has the lowest radius compared to that of NaCl, KCl, RBCl, and CSL. So lattice energy will decrease this way. Kf is greater than KCl, KBr, and Ki when it comes to lattice energy. Li3n greater than Na3n and K3n. This is about lattice energy. Finished? Next. What is the charge on cation and anion? If the charge on the cation and anion is more is the lattice energy. So you can notice this here. Mg3N2. So charge is plus 2 into minus 3. So it will come out as minus 6 here. Well, here it is minus 4, here it is minus 2. So more amount of charge on the cation or anion, more is the lattice energy. And next, hydration energy. Energy released when one mole of a gaseous ion converts to an aqueous ion. So we can write this as Q plus by R plus Q minus by R minus. So lattice energy depends upon these factors. Next, if you notice the ions here, positive ions, Li plus, Mg2 plus, and Al plus 3, as the charge increases, hydrogen energy increases. Same case with the negative charge also. If the charge on the negative side increases, higher will be the hydrogen energy. And if you notice the ionic radii, lithium plus will have greater than Na plus, K plus, and Rb plus. And F minus will have greater than Cl minus, Br minus, and I minus. Next. Dielectric constant. Higher the dielectric constant, correct? More is the solubility and less is the force of attraction. So you can see lithium plus gases will have, size size being increasing towards cesium. When you have a decreasing value, so you can see this gas, if it converts to aqueous solution, this gas converts to aqueous solution. Then down the group, if you go, the size will decrease because aqueous ion of lithium will be much bigger in size. Okay, that also makes the mobility of lithium plus very very weak. So ionic mobility of lithium is very weak compared to that of cesium plus aqueous ion. Next, reducing and oxidizing power. Reducing and oxidizing power mainly depends upon how the metal is converting into an aqueous ion or any element is converting into an aqueous ion. If it is converting into a positive ion, that means this M must be metal. Metal goes through three energies. First is sublimation energy to convert solid to gas. The gas converting into ion, that is ionization energy. The gaseous ion converting into aqueous ion, that is hydration energy. So if hydration energy dominates over the sum of sublimation and ionization, then it is a very good reducing agent, which means it can oxidize to M plus 2 very, very easily. M plus 2 very easily. Okay. Oxidizing power mainly depends upon, ability to give electrons here. Hmm. Check. Now, ability to oxidize the others and reduce itself. Notice x2 plus 2 electrons giving 2x minus. This is for non-metals. First, you need to require some bond dissociation energy to convert into gaseous atoms. That converting into X minus, we require electron affinity, and from there, energy, if it is converting into aqueous solution, energy is released, and that is hydration energy. And if hydration energy is greater than bond dissociation plus electron affinity, then it will go in the forward direction. So He dominates over the other energies, then it becomes a good oxidizing agent. So F2, Cl2, Br2, and I2 are good oxidizing agents. Done? Next, solid to liquid fusion, liquid to gas vaporization. These are the terms. You please remember them. Okay, it will be useful. Next, what is an inert pair effect? You see, right? Inert pair effect is the non-participation ability of ns electrons in any bonds. Usually, this is observed in 13, 14, 15, and 16 groups, especially between 6th and 7th period. The size of the elements is relatively lesser than increasing down the group. So we expect a certain amount of size to increase, but it is lesser than that. This happens because of the poor shielding of inner F electrons, which causes this high Z effective on Ns electrons. That is, if you notice, this is the nucleus and these are all the orbits, correct? If this is an electron present in, P shell or a S shell here, and before that, imagine in this case, there is F electrons. Those F electrons will shield these electrons very, very poorly. Okay. So therefore, if you notice group 13, group oxidation state is +3, but during down the +1 oxidation state is more stable. A minute. Yeah, notice this. This is because of the poor intervening of F electrons. Now, when it comes to group 13, group oxidation state is +3, but down the group, if you notice, it will be more stable with +1 oxidation state. So when it comes to boron, this is more stable in +3 than aluminum, gallium, indium, and thallium. But when it comes to +1, down the group it increases. Thallium will be very, very stable in +1. So much so that if you take TlI3, it is not exactly existing as, some three iodine ions. It is basically existing as Tli plus I2. In fact, to start with, it is actually going to exist in Tl plus and I3 minus. And this I3 minus is the one which will convert into I minus and I2. So it is tellurium with +1 oxidation state present. See, if the question is given only TlI3 like this, do not take it as +3. You will directly take it as +1 in exam. TlOH thrice, here you will take it as +3, but you will show that it is highly unstable. So that will become TlOH, H2 and O2. Ionization energy, boron greater than thallium, gallium, aluminum and indium. Okay, next. Group 14, same logic, +4 oxidation state is more stable and it increases down the group, it decreases down the group. But +2 oxidation state increases down the group, lead shows highest +2 chain. So +4 oxidation state lead compounds are hardly existing, out of which PbF4, PbO2 are mostly existing. These two will not exist only. So PbF4 will be ionized in ionic bond with Pb +4 and 4F minus. PbO2 has a tendency to decompose very easily to become PbO plus half O2. PbCl4 is not existence, PbI4 is not existence. They will always convert into PbCl2 plus Cl2. Okay, next. Usually, if you notice, SnCl4 is greater than SnCl2 in stability, but when it comes to lead, plus 2 is more stable. Similarly, tin is more stable in plus 4, lead is more stable in plus 2. So these are the ones which exist in ionic form, and these are the ones which exist in covalent form when it comes to SNO. Got it? Now notice this one. This is the case you need to understand that how the thallium plus 1 is greater than that and so on. Arrhenius acid base theory and all, I'm sure everybody knows that which is more acidic, which is more basic. I've just written it again just in case if you wanted to check out which of them are acids and bases. Okay. And one last exception out of this is this one H3PO2, H3PO3, and H3PO4. Although this has lower oxidation state, this is more acidic compared to H3PO4. This is the acidic strength. Okay. So H3PO2 will have more acidic nature compared to plus 3 compared to plus 5. Here because after releasing this one H plus, one second. Hello. Ah, no,